Welcome everybody. This is actually the last analysis seminar of this academic year, and it is a pleasure today to have Phillip Isett from the University of Texas at Austin, and he will talk about local energy dissipation for continuous incompressible oil flows.
Okay. Thank you, Camilo, and thank you to the organizers for inviting me. So the plan is to discuss the strong Onsager conjecture. So I want to talk first about what is Onsager's conjecture, where it comes from in the study of turbulence, and emphasize the importance of local energy dissipation. And if you incorporate local energy dissipation into the Onsager's conjecture, you get the strong Onsager conjecture. I'll give you a survey of the previous results related to it, and then I want to give an outline of what goes into the first construction of continuous Euler flows that exhibit local energy dissipation. So that's the plan for the talk. So first, for the motivation part, let's introduce the Euler equations. Here they are. I've written them with the summation convention. So J is repeated. Equation 2 says divergence V equals 0. And they're derived from conservation laws, such as equations 3 and 4. Equation 4 expresses the density, and for density to remain constant, the flux of fluid through the boundary has to be 0. The amount going in has to be equal to the amount going out at any given time. So that's the balance of mass. And then equation 3 is the balance of momentum. The time derivative of the total momentum in omega for any region omega will be the force exerted on omega, which is a force of pressure that's exerted normal to the boundary of omega, plus the flux of momentum that's carried by particles that fly into and out of the region. And equations 3 and 4, if you know your solutions V and P are C1, are equivalent to equations 1 and 2. But notice that equations 3 and 4 make sense even if your velocity and pressure V and P are only continuous functions. So they give you a notion of a weak solution to the equations. Now, you may expect that continuous solutions may have different physical properties from smooth ones. We know that the total momentum is conserved if omega is equal to 0. But they may not, the conservation of energy is not guaranteed. Remember, when you prove conservation of energy, you take the dot product with V, and you have a smooth solution, and you derive the local conservation of energy, which is this divergence form identity. And then it's quadratic and cubic. And then when you integrate this in space, the divergence term integrates away, and you get the time derivative of total energy is 0. So local conservation of energy and conservation of total energy hold if your fluid is smooth, but this requires some regularity to justify the computations, and it's naturally asked how to conserve energy. So Lars Onsager, a physicist in 1949, made a conjecture about this question. He said, first of all, that C alpha solutions with alpha greater than 1/3 must conserve energy. But if alpha is less than or equal to 1/3, he stated that there should exist a solution that failed to conserve energy. Now, why was Onsager, who's a physicist, interested in Hilbert continuous solutions that fail to conserve energy? Well, he was interested in turbulence, which leads you to think about solutions that dissipate kinetic energy, as I'll describe on the next slide. So to get K41 theory, which is the starting point for the quantitative study, we look at 3D Navier-Stokes equations, which has the viscosity that models the internal friction in the fluid. And we're interested in this regime where the viscosity is very small compared to characteristic lengths of velocities. So after you rescale things, this is equivalent to viscosity going to 0. And you want to know what happens as viscosity goes to 0 for a fully developed turbulent flow. And you might think, okay, viscosity causes energy to dissipate, but as viscosity goes to 0, we should see the rate of energy dissipation go to 0. And Kolmogorov's starting point is to say that that's rather that the energy dissipation that's strictly positive, independent of viscosity. So even though the viscosity is going away, you still see energy dissipation. And this energy dissipation rate is the key quantity that governs the statistical properties of turbulent flows in the theory. For example, if you want to know how large are velocity fluctuations in your turbulent flow, they should obey a scaling law that the difference in velocity should scale like distance to the 1/3 over a large range of length scales. And that distance to 1/3 comes because it's the only scaling law with the correct units that you can make with the energy dissipation rate. This is all assuming that there is a positive dissipation rate of energy dissipation. So a puzzle this leaves you with is, how could there be dissipation of energy if viscosity is going to zero? What's causing the dissipation? And Onsager put forth an idea to explain how you can evolve. So he explained his idea as follows. He said, forget about, he explained the idea called an energy cascade, which he explained as follows. Forget about viscosity. Imagine you just have the Euler equations and look at the Fourier series representation of your solution. And notice that because your equation was nonlinear, low wave numbers interact with high wave numbers. So in principle, you could have some energy that starts at low wave numbers, moves to high wave numbers, and it could vanish to infinite wave numbers in a finite amount of time. So you could dissipate energy even with no viscosity whatsoever. However, he observed that only low regularity solutions could behave this way. And he stated that C alpha solutions with alpha greater than 1/3 must conserve energy. On the other hand, he also predicted that your typical turbulent flow would have energy at scale lambda scaling like lambda to the -2/3. So the regularity of those solutions would be exactly 1/3. So that brings us to Onsager's conjecture, which is that C 1/3 is the threshold for energy conservation. Above that, energy should be conserved, but below the kinetic energy. Now, this claim that energy is conserved above 1/3, he had an almost rigorous proof, and that was not published. A rigorous proof came in the 90s by TT, and we understand very well conservation above 1/3. The upshot is you should use L3 based function spaces. And if you have a slightly better than 1/3 regularity in the space-off sense, then energy is conserved. But if you have exactly 1/3 conservation of energy. So that's what we know, we know in the direction of conservation of energy above 1/3. There might be endpoint C 1/3 solutions that fail to conserve energy. That leaves us with the question of, can we prove the existence of solutions with regularity below 1/3 that fail to conserve energy? And furthermore, can we show these arise as zero viscosity limits? Now, let's talk about the zero viscosity limit. What does Kolmogorov's theory say in the zero viscosity limit? Well, if you take the zero viscosity limit, this 1/3 scaling law holds over the whole range of length scales. So that gives you compactness. And so as viscosity goes to zero, you would get a solution to the Euler equations that is C 1/3 because of the scaling law, and it would dissipate kinetic energy. It would not conserve kinetic energy because energy dissipation is independent of viscosity. So the K41 theory implies there should, interestingly, this observation that K41 implies compactness was not noticed until 2012 by Chen and Glim, who showed that weak K41 theory implies convergence along subsequences, and more refined statements have been given more recently by these authors. And another remark is that there is empirical evidence that energy dissipation isn't independent of viscosity in turbulence, but generally it involves forced turbulence, and so it doesn't dissipate away. But besides these remarks, let's just stick to the Navier-Stokes equations and formulate K41 as a conjecture. So it's a folklore conjecture. And we summarize that it as follows. Does there exist a smooth sequence of smooth weak solutions to the Navier-Stokes equation? So this is a question about smooth solutions to Navier-Stokes with viscosity going to zero that have the following properties. So they're smooth, but only the C 1/3 norms are uniformly bounded in viscosity. So they could be converging to something C 1/3. and also they exhibit energy dissipation independent of viscosity. So does such a sequence exist? Can you find flows with Navier-Stokes 0 that are bounded in C1/3 and dissipate energy independent of viscosity? So that's the problem. And when you think about this conjecture, you got to realize that the initial data are not fixed. We're talking about solutions and initial data that are smooth, but becoming increasingly singular as viscosity goes to 0. And so there's a conjecture for about the 0 viscosity limit that should happen, give or take the exact function space in the scaling law. But it has an implication as viscosity goes to 0 for the Euler equations, which is the following. So if we take 0 viscosity limits, we have to realize that there is an important local energy dissipation for Navier-Stokes solutions. Navier-Stokes solutions obey a local energy equality, which shows local energy dissipation because the term on the right-hand side is negative. That shows that energy dissipates locally. And when you take a 0 viscosity limit, if it converges in L3, the limits are Euler flows that satisfy the local energy inequality. So in order for an Euler flow to be a 0 viscosity limit, in order to be physically admissible, it has to satisfy this local energy inequality that expresses local dissipation of energy. And that brings us to the strong Onsager conjecture, which is that not only should there be C1/3 solutions to Euler that don't conserve energy, but there should be C1/3 solutions that locally we find these. Okay, that's the strong Onsager's conjecture. It's a necessary consequence of the K41 folklore conjecture, because if you assume the bound on the C1/3 norm, you have uniformly convergent subsequences by the Aubin-Lyon-Simon compactness lemma, and so it's a consequence of the theory for Navier-Stokes. Also notice that so Navier-Stokes, this theory, if it were correct for K41 were correct for Navier-Stokes, at least for a sequence, then there would be C1/3 solutions that locally dissipate energy. These C1/3 solutions would not necessarily be unique. You need something like Lipschitz regularity to imply uniqueness. So you might be talking about non-unique solutions here. But this raises an already difficult question, which is that are there even incompressible Euler flows that fail to conserve energy? So strong Onsager conjecture is there are C1/3 flows that locally dissipate kinetic energy, but it's not obvious there are any weak solutions that fail to conserve kinetic energy at all. And it wasn't until breakthrough works by Scheffer and Schneemann that this was known, that there are L2 solutions that with compact support or that dissipate kinetic energy. And then these were difficult papers, but a more systematic framework was obtained by Deleuze and Sekeli-Hidi, who showed there are L-infinity solutions that dissipate kinetic energy. In fact, they can have any local dissipation rate that you want. So this proves that there are local dissipation, locally energy dissipating solutions to Euler. But these solutions are not continuous, and the argument faces a major difficulty towards obtaining continuous solutions. So following this work in 2012, Deleuze and Sekeli-Hidi started the pursuit of the Onsager conjecture by showing that there are C alpha solutions for alpha less than 1/10 that fail to conserve kinetic energy. They could show that the energy could be prescribed to be any smooth positive function that you want. And so that they don't locally dissipate kinetic energy, but they do dissipate total kinetic energy and this is for alpha less than 1/10. And this started a series of results. I came in next with improved this result to alpha less than 1/5, compactly supported solutions. And Buckmaster, Deleuze, and Sekeli-Hidi showed that you could also prescribe the kinetic energy in this regime. Buckmaster observed that you can showed that you can improve the regularity to C1/3 minus epsilon at almost every time, and this was improved to L1 in time, C1/3 minus epsilon. I solved Onsager's conjecture in 2016. A key idea came from a paper of Doneri and Sekeli-Hidi, and Buckmaster, Delhi, Sekeli, Hidi, and Bicol also showed that you can still prescribe the total kinetic energy. So none of these results have local energy dissipation. It's always the total kinetic energy that is not conserved. And it turns out the endpoint alpha equals 1/3 is there's instruction to obtaining it from these methods. But what is possible after everything is optimized is to obtain this result where the Hölder exponent approaches 1/3 at small spatial scales at a certain rate. So this is what we know about Onsager's conjecture. It's basically a solution up to the endpoint. And what does it tell you about turbulence? It tells you that these energy cascades that Onsager predicted can really happen. They're really compatible with the regularity predicted for turbulence. So the energy cascades can occur. There's no viscosity, so energy must be dissipated by the cascade process. But that they don't tell you that local energy dissipation can happen. And none of the solutions that I've just talked about are physically admissible because they all fail to satisfy this local energy inequality. They cannot be zero viscosity limits as a consequence. So we want to show that there are solutions that see 1/3 locally dissipate kinetic energy. And local energy dissipation is a much stronger requirement than total kinetic energy dissipation. You can see this already in Burger's. Local energy dissipation in Burger's implies uniqueness, but you can easily construct non-unique solutions that dissipate total kinetic energy in the Burger's case. So you get there's a lot less flexibility if you require the local energy inequality to hold. So the only previous result on local energy dissipation was the one I discussed previously by Deleuze and Sekeli, where they could construct L-infinity solutions with a prescribed energy dissipation rate. And these solutions are not unique. You can have a large family from the same initial datum that forms a bare generic subset of a complete separable metric space. So kind of a huge family of solutions from the same initial data. These solutions, however, are all nowhere continuous. Nowhere do they have positive regularity. So to get to C 1/3, we first need to get continuous solutions. And that's the result I want to talk about today is the first continuous solutions. In fact, C alpha solutions for alpha less than 1/5 that locally dissipate energy. So this is the first result towards the strong Onsager's conjecture, and it comes with a non-uniqueness statement. There's an infinite in the family that has the same initial datum. You can have them share the same energy dissipation measure, d of Vp. So I want this d of Vp, this quantity that's quadratic and cubic. I'll be talking about it a lot. Why would you want them to share the same energy dissipation measure? Well, you might think that the non-uniqueness arises because of information that's lost in the zero viscosity limit. If these were zero viscosity limits, maybe non-uniqueness happens because you lost information in the zero viscosity limit. But perhaps you could recover that information if you knew the energy dissipation rate. The fact that they share the same dissipation measure means that no, you wouldn't expect that to restore uniqueness. And furthermore, the energy dissipation rate can even be zero. So you can have solutions that locally conserve energy and are still highly non-unique. And the non-uniqueness is very severe. It is a Cantor family of solutions that has positive Hausdorff dimension in the energy space. So what does that mean? The fact that it's a Cantor family means there are no isolated points in this family, which means there is no finite precision measurement that can restore uniqueness. You can't do a measurement with finite precision and isolate a unique solution because there are no isolated points. Also, the family has positive Hausdorff dimension. That's interesting, not only because it's a new result, being bare generic does not imply positive Hausdorff dimension. So it's a new result, but the proof of this is by a probabilistic method. Somehow, if you incorporate randomness into the construction of solutions, you get this improved uniqueness where you can have a positive Hausdorff dimension family of non-unique solutions. But I won't talk about the details of that. I'll just talk about the existence. How do you construct continuous solutions with that locally dissipate kinetic energy? But before that, I have to mention that this result has been improved recently by Deleuze and Quan. The exponent has been improved from alpha equals 1/15 to 1/7. And this is using a nice idea of discretizing the Mikado flows of Donner and Sekahidi that were used to prove Onsager's conjecture. Now the open problem is improve the 1/7 to 1/3. That's the strong Onsager conjecture. Okay, so the plan is to go over the existence of continuous solutions, some highlights of the proof. Here's the overview. First, I'll talk about the general strategy of convex integration. How do you construct continuous solutions, in particular using one-dimensional? That'd be cool. So I'll introduce some of the main tools: the Euler Reynolds flows, one-dimensional waves, the Micralocal Lemma, and the main error terms. And then introduce the new ideas to get local energy dissipation for the solutions. This is the notion of dissipative Euler Reynolds flows. And and the notable features are that there's an arrow of time in the construction. So this is the first construction where an arrow of time plays an important role. And this is also the first construction where trilinear energy cascades play an important role. And that's something that has relations to a theory of turbulence by Kriknen called the Lagrangian direct interaction approximation theory. Okay, but first, how do you construct continuous solutions? So the continuous, the key starting point. Yeah.
Ask a quick question. So how you say, are you using some probabilistic structure here? I didn't see that in the outline.
Oh, I'm not going to talk about the probabilistic argument. Is this there? It was a
separate argument, or how does that go?
It's just something I used to prove the non-uniqueness results to get a whole big positive Hausdorff dimension family. I inserted randomness into the construction, and when you insert randomness, you get many non-unique solutions.
And can you do this also with the Deleuze-Quan?
Well, they don't have the you'd have to improve it a bit, but probably.
Yeah, I would say it's probably doable, but yeah, not embedded directly in what we are doing. But I guess you could like like for instance change the sign randomly of some of the perturbations.
That's what I do in my but you have to change the sign randomly of lots of the perturbations, because
but it seems doable, but probably one would have to check the details if it's not like
Okay, thank you. Yeah.
Messing with the combinatorics.
Yeah, that's the idea. So we're just going to construct continuous solutions in what follows, and that's the outline. Okay, so the key starting point is to figure out how to approximate continuous solutions to the Euler equations. So the family of approximate solutions are called Euler Reynolds flows. They're solutions to the Euler Reynolds equations, and they involve it's like the Euler equations with an error R. RJL is a symmetric tensor. And when RJL equals 0, you have a solution to the Euler equation. So it measures the error from solving Euler. And the benefit of the Euler-Reynolds equations is it's easy to construct smooth solutions to the Euler-Reynolds equations. There are tons of them. And it makes sense to use them to approximate Euler flows, because every continuous incompressible Euler flow is a uniform limit of smooth Euler-Reynolds flows, which you can prove by just mollifying the equations. So we're gonna try to approximate Euler flows by Euler-Reynolds flows, and we'll make a sequence of Euler-Reynolds flows indexed by Q. So the qth velocity, the qth pressure, and the qth error tensor R. And the idea is we construct them starting with low frequencies and adding in high frequencies. So we add one frequency shell at a time. So capital VQ is a high frequency correction that we add to the velocity, and capital PQ is a correction we add to the pressure. And after we add these corrections, the error is supposed to get smaller. And we're going to do this over and over. So the error is going to get smaller and smaller when we add corrections. And the corrections are higher and higher frequency, and they get higher, smaller and smaller. In fact, because the errors and the whole series can be summed to get a uniformly convergent series that converges to an Euler flow. So the error is going to go to 0, and the velocities are going to converge to an Euler flow. So that's the idea to generate a sequence like that. We'll just focus on one step of the sequence. So we'll remove this index Q here and just focus on one step where we start with an Euler Reynolds flow and we try to make the error smaller. So we're going to add a correction capital V and add a correction capital P to the pressure. And the idea is after we add these corrections, the new R is going to be smaller. The new velocity will be star, the new will be called P star, and the new error will be called R star. And R star is supposed to be way smaller than the previous error R. So that's the general idea, which sounds very general, but when you try it out, you realize that you run into difficulties, that when you add corrections to the equations, what you're supposed to see is the divergence of a small symmetric tensor. The new error is supposed to be really small. But what you actually see are terms that are not the divergence of a symmetric tensor, or they're the divergence of a symmetric tensor that is not small. So a key point in order to get a small error is the following. First, you have to choose your corrections very carefully so that they can cancel out the old error. And after that's done, you have to solve the divergence equation to get your new error. Only after you solve the divergence equation and choose your corrections carefully does the new error become small. So solving a divergence equation is an important part of the scheme. And how small will R be? Well, my correction is going to oscillate with a large frequency lambda, and I want my error to be, let's say, 1 over lambda. Okay.
Are you always measuring your error in the C0 norm, or do you have to use?
Yeah, there are no interesting function spaces. It's always in C0.
Just C0. Okay.
Yeah.
In space time.
Yeah. So we'll add these corrections, and they're supposed to cancel out the old error, and the new one will be small after solving the divergence equation. We get several different kinds of terms. Some of them are linear, and then some of them are nonlinear, and the nonlinear ones have low frequency and high frequency parts. All of these terms will be size 1 over lambda after we solve the divergence equation. And there's another error term because you have to mollify the velocity field and you have to mollify the stress tensor, and that gives you another error term, which we'll ignore. Okay, so what's the correction going to like? It's supposed to be a frequency lambda divergence-free wave. So it's going to have, following my scheme with Vicol, it's going to have a phase function Ci and an amplitude Vi. And there's a small correction to make sure this thing is exactly divergence free. And besides being divergence free, the phase function is going to be transported by the coarse scale flow. So the high frequency oscillations travel with the coarse scale flow. And furthermore, there's an orthogonality. To be divergence free to leading order, the amplitude Vi has to be orthogonal to the phase gradient. Otherwise, we have complete control over the amplitude and the phase functions. To be more precise, we want it to be frequency localized, so we'll use a Leray projection to make it divergence free, and we'll localize it in frequency. So that's a convolution operator applied to a frequency lambda wave. A tool we'll use is the Micralocal Lemma, which says that if you have a frequency lambda wave and you plug it into a convolution operator, and your convolution operator is restricted to frequency lambda, then you have this expansion. This is a Micralocal Lemma that says that your convolution operator behaves to leading order like a multiplication operator. In our case, with a Leray projection, it's going to act like a orthogonal projection, which is going to act like the identity map because our amplitude is already orthogonal to the phase gradient. So the leading order term will just be the amplitude, and then we have a lower order term, which we have very nice control over. And the proof of this lemma is by Taylor expansion, and it's fun, but I will skip the proof. Okay, so the leading order term is the amplitude, involves the amplitude and the phase function, and we're going to plug that in. It's a divergence-free wave. The phase function is transported along the flow, and the amplitude is always orthogonal to the phase function, and it's localized in frequency. And now let's ignore the correction and just plug in this main term and see that if all the terms can be of size 1 over lambda. So the linear term is the following. Let's see how that works. It involves the advective derivative. This derivative, that's the time derivative along the course scale of the trajectories of the velocity field. And we're scared of hitting the phase function because we'll bring down this bad factor of lambda. But fortunately, the phase function is transported by the flow. So instead, we're only differentiating the amplitude, which is nice and smooth. So this term looks nice and harmless. It's at frequency lambda. And when we solve the divergence equation, we gain a 1 over lambda. So we get the new error is small, like we wanted. And the new error is also, in this case, localized to frequency lambda. So the linear terms are high frequency, but the nonlinear terms have low frequency parts. And they should ideally be treated as follows. We should take our wave and add up the individual plane wave contributions. And the low frequency part happens when you multiply one wave by its conjugate. That's when e to the I lambda c multiplies by e to the minus I lambda c. In that case, the phase functions cancel out, and you're left with the sum of the amplitude squared, sum of vi bar, where vi is the amplitude. Now we control the amplitude, so this can be any positive definite tensor we want. And if we'll control the pressure too, so we can get negative definite tensors also. So we can cancel out any arbitrary tensor r, any error r. We can cancel out that thing pointwise by choosing p and choosing the amplitudes appropriately. So we cancel out the low frequency part of the error pointwise. We absorb it into these amplitudes. The only constraint is that our amplitudes are still subject to the orthogonal to the phase gradients. Now, that was the low frequency part. There is a high frequency part of the error, which is scary because it involves the divergence hitting the frequency lambda waves, and that brings it down a bad factor of lambda. You have to hope that somehow this cancels out, and this will cancel out if what happens? Your amplitude vi has to be orthogonal to the phase gradient of the other wave. So every amplitude should be orthogonal to the phase gradient of every wave. So an idea would be to make that happen, you can make every phase gradient point in exactly the same direction, and then make every amplitude point in the hyperplane orthogonal to that direction. So if that's the case, then this high frequency error term will cancel out. The difficulty that leaves you with is if they're all the amplitudes are pointing in the same hyperplane, that means when you try to cancel out the error, you can only cancel out the restriction to one hyperplane. And you'll have to do 3 different hyperplanes in order to cancel out the error. So we can cancel out the first hyperplane with one oscillation, but then we have to start over, use a bigger lambda, use another series of waves to cancel out the second hyperplane. And then we use another series of waves with an even bigger lambda to cancel out the third hyperplane. After that 3-step process is over, the error is finally smaller and you can repeat. So the error becomes smaller after using 3 different waves and 3 different hyperplanes with 3 different lambdas, and repeat with higher lambdas. The error goes to 0, you get continuous solutions. So that's the outline of how to get continuous solutions, but now I want to get solutions that satisfy the local energy inequality. Okay, so here's where the new things start to occur. So how do you get solutions to satisfy this local energy inequality that imposes more rigidity? The starting point idea is to think, what if we relax the local energy inequality?
Sorry, Phil,
the same way we relax the Euler equation.
We lost part of the things that you were saying because the connection went out.
Oh, okay. Thank you. So we want to now create a scheme where we can get the local energy to the inequality to hold. So I'll start talking about the new ideas for doing that. The starting point is, how do we get this local energy inequality to hold? Well, one, you could think maybe we would relax the local energy inequality, allow for some f here on the right hand side, for some r on the right hand side. Maybe if we allow for an f on the right hand side, and then we do a scheme where we make r go to 0 and we make f go to 0 at the same time, that then we'll get 0 on the right hand side in the limit. Okay, so that's not actually going to work, but it's on the right track. The idea is that you have to relax the local energy inequality, but you have to relax it in a particular way. And the way is the following. At least it's the definition of a dissipative Euler Reynolds flow. So the right-hand side of the local energy inequality, instead of being 0, it is the following form. So there are 3 error terms now, r, kappa, and phi. And the right-hand side is the advective derivative of kappa. That's the unresolved flux density, plus divergence of v contracted with r. So there's a coupling. The same error tensor r is used here. And also plus the divergence of unresolved current phi. And the idea is we want all kappa and r and phi to go to 0 at the same time. And I define the dissipation measure to be the right-hand side minus the left-hand side. So it's something mu that's non-negative. So we want to make kappa and r and phi relaxed local energy inequality. And so we're going to add these corrections to get v star and p star. But the new dissipation measure is going to be with a new kappa, a new r, and a new phi that are all smaller than the old ones in the C0 norm. Okay, so that's the plan. Now, when we add the corrections, what happens to this dissipation measure? Recall that the dissipation measure is quadratic and cubic terms, so there is going to be a whole slew of terms. Some of them are going to be bilinear and some of them will be trilinear, and they all should be bounded by something of this form with the new kappa, the new r, and the new phi on the right-hand side. Let's look at those error terms. Here's the linear ones gathered here. Here's one of the quadratic ones. The next one's quadratic. Here's another quadratic one. And this last one is cubic. So we have a whole bunch of terms. This is most of them. And let's talk about how the linear one goes, just to get a sample. So when we look at this linear term, how can we treat it? We can relax local energy inequality. I first take the velocity field and I mollify it. And mollifying this velocity field introduces an error term that has the right form. It's the advective derivative of some kappa plus divergence of some phi. Now, after I've modified it, I can, and something good happens with this linear term, which is that I see the transport to error that I saw previously. And this transport error is left-hand side of the Euler Reynolds equations. So I see the new error actually appear from this term, at least the linear part of it. And I can move this divergence to the outside. So I have a term that looks like divergence of v contracted with the error, the new error. That's exactly the form of the error that I wanted to see. And everything else that's left over has this nice structure that it has restricted to frequency lambda. And because it's restricted to frequency lambda, I can take all this stuff, absorb it into the new current, and then the first to this term in the relaxed local energy inequality. So when you look at the terms, they have this good structure where you see the coupling of the new error with these. It appears when you dig for it, you get the right structure. Let's talk about how we get rid of these new error terms kappa and phi. So the density kappa and phi, we need to cancel them out and make them smaller. We're going to first talk about phi. And this is a trilinear problem. We want the trilinear interactions to cancel out the current phi. So here are all this trilinear actions. We're going to restrict to a certain trios that give you low frequency interactions. So we're going to use the low frequency interactions to cancel out the low frequency part of phi. So the low frequency interactions happen when all your phase functions add to 0. And in that case, you just get the amplitudes, a trilinear expression, the amplitudes. We control the amplitude part of phi pointwise. And then we just have to worry about the high frequency error terms. The high frequency error terms turn out to be okay because of the orthogonality. So they can be absorbed into the new current. So we're absorbing the old current into the amplitudes by solving this cubic equation. Now we want to cancel out kappa. Okay, canceling out kappa, we take v squared and this nonlinear term, and we yet again go separate low frequency versus high frequency. The low frequency stuff we want to cancel out kappa. Frequency object we control has to be positive. We never said kappa was negative. So we can only cancel out something negative with something positive. So the only choice we have is to subtract something. We subtract the function e of t. After we subtract e of t, this thing we're trying to cancel will be negative. The price we pay is that we have to add what we subtract. But we have the freedom to do that as long as we respect the arrow of time. So this is where the arrow of time comes into play. The function that we subtracted is kind of a rate of dissipation, and we need it to be non-increasing in order for it to have the right sign to be absorbed into the local energy inequality. So as long as we respect the arrow of time, then we can subtract this function e of t, and we can cancel out the unresolved flux density. Well, that's true, except that there is kind of a conflict. We said we're trying to cancel out kappa, but we also said we're trying to cancel out r, and there's a conflict between these two equations because the positive term here is half the trace of the positive definite term here. And okay, so there's kind of a linear dependence between these two equations. The only way, but we can make them compatible with each other as follows. There's a unique choice of pressure. So if we set the pressure pointwise to be the following function, then this equation becomes half the trace of the first equation. So solving the first equation implies the second. So we cancel out r and cancel out kappa at the same time if we choose the pressure in that way. There's also another conflict though, because we wanted to cancel out phi as well with some of the amplitudes. And these amplitudes that we're using to cancel out the phi are actually entering into the equation when we try to cancel out the r, or the first component of r. So the idea is the following: how do we cancel out phi and r at the same time? Well, those waves that we use to cancel out phi, we can extract them from the sum and put them on the right-hand side. And then, so we can then absorb these amplitudes into the ones that are being used to cancel out the r. That strategy will work as long as phi is a lower order term. So as long as phi is a lower order term, the current is lower order, then we can absorb them into the amplitudes. We can treat this sum as a lower order term. However, that actually threatens the success of the iteration to require that phi is lower order than r, because you have to, when you do this iteration, you're doing it over and over, and you have to ensure that phi is always lower order than r. And when you look at the new current, you start seeing dangerous terms that are not lower order. They point in the correct hyperplane, like this one this is part of the pressure that you did not eliminate because you were restricting to a hyperplane. This term is too big to be lower order. And if it were really that big, then we wouldn't be able to succeed, but something great happens, which is that even though the term is too big to be lower order, the divergence of this term has a special cancellation. When you take the divergence, you see this factor of lambda and the divergence, but there is a special cancellation from the algebraic structure of the setup that the phase gradient and the amplitude actually cancel out when you contract them with the remaining tensor. And because of this cancellation, the leading order term here is 0, and you can apply an inverse to the divergence to absorb this term into the new current. So it was too big at the start, but the divergence had a special structure, and you could absorb it into the new current. And then, so every term either has the structure where it has a good divergence, or it is already small and can already be absorbed into the current. And thanks to that, the whole scheme can work. And that's all for my presentation today.
Thank you. Questions? So I have one question in the solution of the Onsager conjecture. Something that played a major role is of course your idea of cutting off gluing solutions of the Euler equations so that you restrict the temporal support of your Reynolds stress to intervals of time over which you can meaningfully solve the transport equation, right? And of course the other side of the ingredient, I mean the other important ingredient is these Mikado flows that have a very little interaction. So one of the things that one of the things that that Yunju and I seem to notice is that it's not so clear that the gluing technique is going to work nicely with the idea that you would like to have also an energy inequality. In other words, if you're trying to glue, for instance, two solutions of Euler that have essentially the same energy, when you're, I mean, in the gluing region, certainly something is going wrong with the energy inequality. Have you thought in that direction? So do you have any sense of whether the local energy inequality might be made robust with a gluing argument?
Yeah, I kind of I haven't thought maybe as much as I should about that. I did notice that like the cutoff regions where the gluing happens is a problematic region, and I didn't see any way to fix that. So it wasn't obvious how to use the Mikado flows without the gluing, but I did have one construction available that actually did work, so I stuck with that one. Mm-hmm. One thing that's interesting is that the Beltrami flows don't seem to work with this. So the Beltrami flows that were used for the 1/5 results also don't seem to be too compatible with this scheme, but that's a different reason, because they don't need the gluing. Because if you could use them, you would have a way to improve another way to improve the 1/15. But mm-hmm. In that case, the problem seems to arise because the cubic interactions that you use to cancel out the current are 0. Mm-hmm. Because the pressure just cancels that. You introduce a term in the pressure that just cancels them exactly. Mm-hmm. Yeah. So yeah, I don't know if I kind of, my feeling is that the gluing it doesn't seem to cooperate with this local energy inequality, but I haven't thought about it as much as I could. Mm-hmm. Yeah.
Yeah, that is our impression as well, that it doesn't cooperate that well with that term. Yes. Any other questions? Okay, so if not, thank you, Phil, for the beautiful talk.